Let's talk about the vanishing gradient problem. As the neural network goes deeper, gradient can become extremely small, slowing or even stopping learning. In this presentation, we will see what causes this, its effect on training, and the key solutions that help maintain stable learning. Avi, could you show the next slide? Let's start with a quick introduction to this concept. As at the heart of the training neural network lies gradient design and optimization algorithm that helps a model learner by adjusting its initial weights in small steps to reduce the error or what we call the loss. We can think of it like rolling a ball down the hill. The ball represents our model and the hill surface represents the loss function. The ball keeps rolling downhill, adjusting its direction to reach the lowest point. That's where the error is minimum and the model performs best. Now, while the process works quite smoothly for small or simpler network, deep network, those with many layers face unique challenges. As we pass a gradient backwards through many layers during training, sometimes the gradient values shrink drastically. This is called vanishing gradient problem. Other times they grow uncontrollably large. That's the floating gradient problem. Both of these make it difficult for the network to learn effectively. When gradient vanish, the earlier layer stops updating. It's like the learning signal fades away before it reaches the start of the network. When they explode, the weights become chaotic and the model becomes unstable. So just like if a ball gets stuck in a flat region and can't roll further, the learning process can also stall due to vanishing gradient. To understand why this happens, we need to look more closely at what goes on during backpropagation and how activation function affects the gradient, especially in deep multi-layer architecture. Abhi, could you show the next slide? Now, what is vanishing gradient? The vanishing gradient problem is a fundamental challenge that arises during training of the deep neural networks, particularly during backpropagation. In this process, the network calculates gradients for derivative to adjust its weights and minimizes the loss. However, in very deep networks, as these gradients are propagated backwards from output layer to the earlier layer, their values often become progressively smaller. To visualize this, imagine trying to pass a message through a long line of people when each person whispers it to the next. By the time the message reaches the first person, it's barely audible or completely lost. Similarly, as gradients travel backwards through many layers, their strength diminishes, and by the time they reach the initial layers, they're almost zero. This means that the earlier layers stop learning effectively because their weight upgrades have become extremely small, sometimes so tiny that they make no meaningful change at all. As a result, the overall learning process becomes very slow, or in some cases stops entirely. The problem is especially common in networks using sigmoid or tangent activation function. Both of these functions output values between 0 and 1 or -1 and 1 for tangent. When we multiply many such small numbers during backpropagation, the result becomes exponentially tiny, just like repeatedly multiplying fraction. In essence, the signal that guides the learning fades away. As it moves backwards through the network, this is what we refer to as vanishing gradient problem. Ati, could you show the next slide? Let's now understand why the vanishing gradient problem occurs. During backpropagation, the network calculates errors at the output layer and sends that information backwards through each preceding layer to adjust their weight. At every step, each layer multiplies the incoming gradient by two key factors, the derivative of its activation function and its weight matrix. Now, where's the problem begin? If the derivatives are small, as in the case of sigma activation function, whose derivative can be at most 0.25, then with each backward pass, these gradients get smaller and smaller. After several layers, the product of many small numbers becomes exponentially tiny. You can imagine this like passing a ball through series of slightly sticky tubes. Each tube slows the ball down just a little. After few tubes, it still moves, but after many, the ball almost stops. Similarly, as gradients go backwards through many layers, they lose strength until the earliest layer receive almost no learning signals. This leads to what we call exponentially shrinking gradient. As a result, the early layer, which are responsible for learning the most basic features such as edges, texture, or shapes, barely update at all. Meanwhile, the deeper layer, closer to the output, may still learn, but the network as a whole struggles because the foundational layers are effectively zero for them. There are three main reasons behind this. A small derivative of activation function like sigma and tangent, and these compress the output into narrow ranges leading to very small gradient. Second, the deep network architecture where gradients are multiplied repeatedly across many layers, creating an exponential decay effect. Third, poor weight initialization where the starting weights are too small or uneven, worsening gradient shrinkage. In summary, as gradients have to travel through multiple layers before reaching the start of the network, the earlier layers receive almost no signal to adjust. This is why Uh, when a vanishing gradient problem primarily affects the initial layers, preventing them from learning effectively and limiting the performance of the entire. Okay, will you show the next slide? Now, how can we identify? Identify the vanishing gradient problem early is crucial because it can save a lot of training time and prevent wasted computation. There are a few clear signs that help us detect it. At first, if you observe that the model weights are converging towards zero or the gradient across the layers become extremely small, that's a strong signal that the vanishing gradient may be occurring. Another clear indicator appears in the training curves. If the model's performance metrics stop improving after several epochs, or if the loss function fails to decrease significantly, it suggests that the model is struggling to operate its parameter effectively. Essentially, the learning process has slowed down or even stalled. A more analytical way to detect this through visualization tools by plotting gradient histograms or gradient norm distribution, we can observe how the gradient values behave across layers. If most of the gradients are clustered near zero, that's a strong confirmation that network is experiencing vanishing gradient problem. In simple terms, it's like the model is stuck on a flat surface. It knows the direction it needs to move, but the signal guiding it has become too weak to progress. This means the earlier layers are barely learning, while later ones may still update slightly. By keeping an eye on this indicator, we can identify the issue early and take corrective measures before the model training efficiently drops.